So can get in the mood after yesterday night extravaganza. Where is my mate? Hey. um, okay, good. So it's all me. Uh, right, so I'm gonna give a couple of lectures about, well, Lisa science and Lisa sources. And of course, I have that's my own biased version of the story because Lisa, a big part of what we are doing with Lisa is very relevant for particle physics, for cosmology. So trying to detect stochastic background from the early universe, for example. I'm completely ignoring that part. So I'm talking only about astrophysical sources. So in particular, mostly compact binaries. So stellar mass binaries, black hole binaries, supermassive black hole binaries, extreme acceleration spirals, and all this kind of stuff. Okay, so that's just a disclaimer. I'm talking about science that we do with astrophysical sources, not cosmological ones. Okay, with Lisa. But that doesn't mean that it's the most important bit of science. It's just the bit of science that I know. Okay. Right. So you already saw this plot yesterday, or maybe even today. I don't remember exactly. This shows essentially the sensitivity curve of whatever version of the Lisa detector this is, but it's pretty close to the nominal one that we have now. So you have frequency on the x-axis and characteristic strain on the y-axis. Okay. So I assume, you've been here for 4 weeks, so I assume you're familiar with gravitational wave strain and all this kind of stuff. I will have some formula later on just to refresh the memory, but very basic things. And here you see a variety of sources, right? So I think Martin showed this plot, right? You see, so these are in spiral and supermassive black hole binaries. Okay, of course, sources are pictured in the frequency domain. And so you see that, a month before merger, they entered the Lisa band, or a few months before merger, and then the spiral and merging band. Okay, so these are evolving signals and very high SNR, but you have a whole other bunch of stuff. So these harmonics that you see down here are extreme acceleration signal from an extreme acceleration spiral. So you have like a compact object like a stellar mass black hole orbiting around the supermassive black hole. All these dots here are compact binaries in the Milky Way, in particular white dwarf binaries, but we also expand neutron star binaries and black hole binaries. And these are also black hole binaries of the type that the ones that are detected by LIGO that are also, turns out they're also interesting Lisa sources. So you see we have a variety of sources, and what I'm going to do is to talk about, let's say, sources involving a small object, either compact binaries and extreme acceleration spirals in this lecture, and I will focus, in the second lecture, I will focus about supermassive black hole binaries, and I will tell you a little bit more of their, formation and evolution, the dynamics, the stuff that Neil was referring to earlier this morning, okay? Right, so just to, a very simple heuristic scaling that I like to give so that you can easily get put sources on a plot using this very simple reasoning, right? So you can of course get the strain of a gravitational wave if you solve linearized Einstein equation, and you do all the math, you do your homework, and you get the formula, the quadruple formula. But you can actually think at the scaling in a very heuristic way, right? So what is the strain of a gravitational wave from a binary? So suppose your binary is formed of two compact objects, like two black holes. Those are defined by their Schwarzschild radii, right? And the size of your binary is the semi-major axis of the binary, A. Okay. So, and at the first order level, the perturbation of the matrix that you do is of the order of the size of the object over the size of the system, right? So that gives you essentially the Schwarzschild radius over the separation of the binary. So that's the size of the perturbation, right, at a linear order. Then that perturbation, of course, has to propagate from the black hole, well, technically from the far zone, but from the black hole to the observer, that is me at the distance r. So it gets damped by another factor r over r, big R over r. And now you can actually express A as a function of frequency by using Kepler's law. And what you get is this formula here, which if you notice, you know, besides not having a chirp mass here and a numerical factor, is the correct scaling that you get by solving linearized Einstein equation. Which is not surprising, because when you solve linearized Einstein equation, you solve a linearized problem, and what I did here is just a linearized order of magnitude reasoning. So it's in principle very simple. So what you can do, then you can just substitute typical astrophysical quantities. So for example, you can express this thing as a function of solar masses as a function of a distance in megaparsec, and you find that this train is formidably small. Okay, and we know that this is the problem for detecting these sources, right? So it's of the order of 10 to the minus 20, mass in units of solar masses, and it scales with the inverse of the distance expressed in megaparsecs. Then of course you can also think, okay, what is the highest frequency at which these two black holes emit? Okay, well, with a factor of a few approximation, is the contact frequency of the two horizons. It's actually the last stable orbit, but there's a factor of 3 difference or so, right? So and they are traveling essentially at the speed of light, a fraction of the speed of light at that time. So the maximum frequency of merger is essentially the speed of light divided by 2 pi r Schwarzschild within a factor of few, okay? And that gives you, 10 to the 4 in units inverse solar masses. Actually, the last stable orbit for an equal mass for a test particle around a massive black hole is 410 to the 10 to the 3 in units of inverse solar masses. So, but within a factor of 2, we have the right number. So and now you have the amplitude, you have the frequency, and you can just play around with number, okay? And you can take your favorite binary and you can compute what is the typical frequency and what is the typical amplitude of the source. And you can, so this is very relevant, because we have detected black hole binaries and neutron star binaries actually as well with LIGO, but we know that there is a whole range of astrophysically interesting sources, okay? And this is what I wanted to show in this cartoon here. So this is essentially a cartoon, in fact, of the known, let's say, and unknown parameter space for black hole binaries in the universe as a function of mass. Okay, so this ranges from few solar masses, where we think is the lowest limit of at least astrophysically formed black hole. There might be black holes from inflation relics, whatever, from cosmological origin, but we are not talking about those here. Then we know that there are stellar mass black holes in the universe. We observe them in X-ray binaries. We observed, so this is I just have GW15914 here as a source, but we observed like 5 or 6 of them with LIGO, okay, and they all fall in this mass here, mass regime here. So this is 10 to 100 solar masses. On the other side of the plot, there are supermassive black holes, which are the topic of tomorrow's lecture. And we see a variety of them in the universe. They typically reside in the center of galaxies, right? And we measure them from, let's say 100,000 solar masses up to several billion solar masses, okay? So this is another population of black holes that we know. There is a gap in between of about 3 orders of magnitude, and this is the realm of intermediate mass black holes. And these are more, a little bit more up in the air, right? We don't have any secure detection, and the problem is because they are really hard to detect. It's not, it's probably really a selection bias and observation bias, the fact that we don't see them. It's not just because they're not there. The fact is that these stellar mass black hole, they are numerous enough that we can have many of them in our own galaxy. And in fact, before the LIGO detection, the examples of systems that we knew were stellar mass black hole from X-ray binaries are objects that are kiloparsec away in our galaxies, right? Whereas these intermediate mass black hole are likely, for example, the seeds of the supermassive black hole that we see today in galaxies. And the reason we need those, because we don't know how to form a billion solar mass black hole from scratch. You need to form something that is smaller, and then accrete mass and make it bigger along the cosmic history, okay? So, but this means that, the seeds of the black holes reside the supermassive black hole reside here, and then they grow along the cosmic history there, right? So in a sense, there is a supermassive black hole in every galaxy. The abundance of these intermediate mass black hole might be of the same order of the abundance of the supermassive black holes. So it means that, to see an intermediate mass black hole, you have to observe it like in the core of a dwarf galaxy, but this might be several megaparsecs away. The influence radius of this intermediate mass black hole is extremely small, so it's very hard to detect. So there are tentative claim of the existence of these objects, but it's pretty much unexplored territory up to now. Okay? Yep. Here, RGG 118. Well, more or less is 5 10 to the 4. So well, I mean, here things become a little bit blurry, right? So there are papers where you can find compilation of hundreds of black holes between 10 to the 5 and 10 to the 6 solar masses. But this doesn't mean that they measure the mass of those black holes. It means that, they, for example, they see some X-ray activity from the nucleus of a dwarf galaxy. They can, they assume that it's a accreting black hole. They assume some relation between the, accretion rate of these objects and the luminosity, and then they place some masses with error bars that are, half a order of magnitude or so. Okay, so these are, they are secure detection in a sense because, there's nothing else really that can power those sources, but, the estimate of the mass can fluctuate by an order of magnitude. So, but there are several now. There are really many black holes that are, say, measured in the range 10 to the 5 to 10 to the 6 solar masses. But going beyond that, going lower in mass is very difficult. No, that's not just a cartoon. That doesn't mean anything. It's just for showing what is the mass range of these possible seeds, which is like from 100 to several tens of thousands solar masses. No, uh, whatever function you like. Usually people like Gaussians, so log normals. No, we don't have any. I mean, we don't have any real model for those. I mean, there are, okay, the models have so many free parameters that you can make whatever you like out of them. Okay, um, just another word about intermediate mass black hole. You might have heard about ultraluminous X-ray sources. So those are, X-ray sources that have a luminosity of like 10 to the 40, some of them and above, ergs per second, and this is way below the Eddington limit for a stellar mass black hole. So they have been historically proposed to be intermediate mass, accreting intermediate mass black holes. Way above, sorry, did I say below? Way above, okay. So the Eddington luminosity for a 10 solar mass black hole is 10 to the 39 erg per second, okay. So these emit 10 to the 40, 10 to the 41. So they've been inferred to be like either a stellar mass black hole accreting super Eddington rate or an intermediate mass black hole accreting below Eddington, right? However, the interpretation of intermediate mass black hole has been questioned several times, and in particular in recent years, there's been a detection, for example, of a pulsed ultraluminous X-ray source that is actually powered by a pulsar. So this is a source that, where we know that the accretor is less than 1.4 solar masses, is a pulsar, and the total luminosity is, above 10 to the 40. So it's very hard to claim that, something is an intermediate mass black hole just because the apparent accretion rate is above the nominal Eddington rate for a stellar mass black hole, right? So I would take any claim of, existence of intermediate mass black hole from ultraluminous X-ray sources with a grain of salt, okay? And I'm already running like 10 minutes behind schedule. That's good. Anyway, so once you know that, there is an interesting range of astrophysical objects, you have these scalings, you can populate a plot like this. Okay, there is a nice version of this online from Christopher Berry and Chris Moore, where you can actually, you can go online, you can insert your favorite detector, you can insert your favorite sources, and you generate a plot, which is actually not as nice as this one, but you can play around with it. But now you see, for example, right, from the scaling that we saw before, there for stellar mass objects, so if you take a 10 solar mass black hole at 100 megaparsec, you know that H is 10 to the minus 21, the frequency is around kilohertz, right? And this is the realm of ground-based detectors. And in fact, we detect those sources with the LIGO-Virgo interferometers, right? Now, if you now take a million solar mass black hole binary and put it at cosmological distance, say 10 gigaparsec, redshift 2, redshift 3, okay? So the strain, you see, is much larger. It's 4 orders of magnitude larger, but the frequency is below, is of the order of a millihertz. So there's no way you can detect this from the ground, right? So that's why we want to put, oh, I should drop the E here. we, we want to put an interferometer in space, because, if simple, you know, so simple thought is like, okay, if I make an interferometer bigger, I can detect bigger things, so lower frequencies, right? And this is how it works, in fact. And so that's why we want to do LISA. And, if you just push up, again, the mass to billion solar masses, you see that the strain is even bigger, and the frequency is sub-microhertz. And this is the realm of pulsar timing, for which now you know everything from the lectures that you heard this morning and yesterday. So I might touch a little bit on this, but I will focus mostly, well, almost entirely on the LISA band, okay? Right. So let's have a look at the type of sources that you can see with LISA, okay, type of binaries. Well, so this is, you should know all of this pretty easily. So, you can take a binary system, you can define its energies is just the Newtonian, let's say, energy of the system, and you can work out what is the emission of gravitational wave with the quadrupole formula, etc., and you can actually define what is the energy rate at which gravitational wave take away the energy from the system, which is this function here, okay, and was, I think, done by Peters and Matthews first in the 60s. So you can equate now the d in dt that you have from gravitational radiation with the variation of energy of your system, and you can change variable from the energy to the separation, and you can get the evolution for the semi-major axis of the system under the assumption that the system is emitting gravitational waves only, okay? And you have this formula here, and it's a function of this f field, which is a stiff function of frequency. So if you have of eccentricity. If you have a very eccentric binary, you emit gravitational waves, you emit more gravitational wave per cycle, so your actual shrinking time becomes smaller. But now you can actually change variable from the semi-major axis to the frequency, and you get this other formula here, which tells you essentially the drifting frequency of a gravitational wave source as a function of their parameters. Now, there are, this was already shown today, and I assume that you already seen in other classes. So there are a few interesting features of this, which I'm going to use to just classify LISA sources, which are the following. So there is a proportionality with mass, okay, to the 5/3. So at a given frequency, you see that low mass binaries live longer, okay, because their frequency drift in time is smaller, okay. So smaller binaries live longer in band, okay, or live longer at a given frequency. Then you see that there is a huge dependence on the frequency, and so for a given mass, low frequency binary live much longer. So if you have a binary at a very low frequency, it's going to stay there essentially forever. Okay, and as you move in frequency, you have what we call the chirp, right? The time the binary spends at a given frequency becomes shorter and shorter, and then you have this whoop, right? The chirp that you hear with when you convert the LIGO signals into sound. And then also there is right, it's not written explicitly here, but there is a redshift dependence. So the observed frequency is actually redshifted with respect to the emission frequency by the factor 1 plus z, right? So high redshift binaries are actually observed at lower frequency, which is, I don't know if I have it, yeah, which is important. Oh, that's cut out. Okay, let's see how serious is that. Which is important because if you have a binary, for example, a redshift 3, that emits here, if you put it at redshift 30, actually the signal that you get on the ground is shifted by an order of magnitude, so it gets down here. Okay, so it becomes not observable anymore. Okay, so the redshift dependence, even though it's only 1 plus z, is an important one. Okay, so but now, okay, we've seen this formula that is very simple. But we can use it to actually divide the LISA sources in two subfamilies. So we have massive objects that are in spiraling and merging, okay? So the frequency is essentially set by the most massive object, and here we have supermassive black hole binaries and extreme mass racing spirals from this in this family. So these are sources that are essentially, let's say, you know, in general, not persistent, okay? The supermassive black hole binary enters into band at some point, it evolves and it merges, okay? So these are bursting sources, if you want. An extreme mass racing spiral lives longer in band, but still it evolves during the mission lifetime, and you know the compact object is going to plunge into the massive black hole in a finite time. So light objects that are far from coalescence are monochromatic systems, meaning that they don't evolve. They're not monochromatic if they are eccentric, but they don't evolve significantly in frequency along the lifetime of the observation, along the time of observation, or they are slowly spiraling, okay? And this is another family of sources, and essentially it collects all the compact objects, like especially white dwarf binaries in the Milky Way, but also the black hole binaries that we detect with LIGO. I mean, some of them at the higher frequency end are going to sweep through the detector band, but the vast majority are going to be emitting like a quasi-monochromatic source for the duration of the mission. Okay, so we have these two family of sources. Right, so what I'm going to discuss today are essentially, well, light objects of this sort, and then I will talk about extreme mass racing spirals, okay? Let's talk about galactic binaries. So this is actually from the gravitational universe, which was the defining document of the science that we wanted to do when we proposed the ELISA detector to the European Space Agency. So we wanted to detect galactic binaries because there is a number of things that we can do with these objects, right? We can, we want to know how many compact binaries exist in the Milky Way, what is the merger rate of white dwarf and neutron star and massive black hole in the Milky Way, and how it relates to the events of other explosive things that we know. For example, you probably know that one of the leading explanation for type 1a supernova is the merger of white dwarf binaries. Okay, so can we measure that with least in the Milky Way and compare with the supernova rate to see if they match up or not, and this kind of thing. So what we can do a lot of science about mass transfer in white dwarf binaries, because some of the LISA sources will be close enough that there will be transferring mass from one star to another, so we can study that process, etc., etc. So there is a whole bunch of scientific reasons why you want to detect these systems. And well, one of the reasons why we are targeting this system is that we know that they are there. So we see some of those binaries in the galaxy, and actually we can compute for some of them the characteristic strain, because we know roughly the parameters of the system. We know that they emit gravitational waves because they are compact binary, and we can put them on a plot with the sensitivity of LISA like this, so we can compute the two polarization strain of the system and compute what is the signal in the LISA detector. And you see that we have like about 15 systems more or less that we know are going to emit gravitational waves in the LISA band. So in particular, HM Cancri here is a very interesting case. So what's the reason why? So you see that you have a large error bar on this, right? So why do you think this system doesn't? So what might be the reason why the error bar on that point is actually smaller than the size of the point? Higher frequency. Yeah. Okay, that's partly the reason. Yeah. So why the higher frequency? What would higher frequency allow you to measure? Chirp, right? So in fact, this system has a measured chirp. So from the chirp, so you can measure, the masses of the system, right? So they have a very nice determination of the mass, but that's not good enough, right? Because even if you know what is exactly the mass of the systems, there are other things that you need to know in order to know exactly what is the strain of the source on this plot, right? You need to know. Thanks. You need to know the distance. If you want to know the signal in the detector, you need to know also the inclination, right? So it turns out that this system is actually, only like a few hundred parsecs away. So you have actually a parallax measurement. So you know exactly what the distance is. And actually is close enough that you can, I think, directly resolve the orbit of the two objects or something like that. So you know actually what you see, what is the ellipticity of the orbit, so you know the inclination exactly. So for this particular system, so essentially you know everything. You know the masses, you know the distance, you know the inclination. So this is a perfect, what we call verification binaries. Okay, these systems are extremely important for LISA because look at this system here. So this has like the signal to noise ratio of the system is going to be like order of 100, let's say, right? And we know essentially exactly what the amplitude of the wave should be. So this means that you can use the system to calibrate the performance of your detector of at the 1% level, which is extremely important because you're just putting something in space, then you hope, you want to calibrate it, you hope it works. You cannot really go there and tweak anything, right? So it's important to have calibration sources for your detection. Okay. Oh yeah, sure, sure. Exactly. Yeah. Yeah. We've let's see. To some extent, to some level, yes. But I'm gonna talk about these sources later on, so we can go back to that later. Um, you can probably actually use LIGO to calibrate LISA in retrospect years later as well. I wouldn't give too much credit to that statement after hearing real talks about. I mean, it's in principle, okay. But yeah, we can we talk about that later. Right. So let's see how many such binaries we expect in our galaxy. Okay. And here we go back to this magic formula here. Uh, so the binary merger rate in the galaxy is estimated to be at this level. So you have like a merger every 100 to 1,000 years. Okay, a merger of a binary system, right? Of mostly wide dwarf binaries. Now we remember now this formula. So well, we can just actually compute the number of sources emitting at each frequency just by multiplying the merger rate by the differential evolution in time of each source, right? So the NDF is equal to the NDT times the TDF. And this is proportional to f to the 11th third, okay? And then you can actually plug in numbers and you can come up with this formula here, which is the time that a source emits at the given log f, okay? And you see this is of the order of 10 seconds. You have the chirp mass of the system to the minus 5 third, and you have a frequency in units of 100 hertz to the minus 8 third, okay? So let's say the lower frequency of LISA, let's take it like 0.1 millihertz as a figure of merit. So let's see what we have now. So our merger rate is of the order 10 to the minus 2, 10 to the minus 3 per year. So it's like 10 to the minus 9 per second, okay? So 10 to the minus 9 times 10 seconds here times this f dependence here at 10, if you compute it at 0.1 milliards, give you 10 to the 15, 10 to the 16. So if you put the three numbers together, you get 100 millions. And there's where you get essentially more or less, and this is typically also the frequency at which you form these systems. So that's where you get the typical number. We're gonna see the signal from 100 million wide dwarf binaries in the Milky Way. So that's exactly how you compute that number. Okay, you know the rate, you know the frequency drift, and you know what's the number of systems. This is computed from supernova. Yeah, we don't really know what is the actual merger rate of these systems. So we estimate of the order of 100 million of this system in the Milky Way. So that's a lot of sources for a single detector, right? And you can play around with other sources, and you can do actually yourself similar calculation for neutron star and black hole binaries. So all you need is a merger rate, And now we have merger rate for those, right? You know that for black hole binaries, typical merger rate is probably around 100 per gigaparsec cube per year from LIGO measurement, right? Whereas is likely a order of magnitude larger for neutron star binaries. So you can use those estimates from LIGO and actually compute, so computing then what is the merger rate for a typical Milky Way-like galaxy, plug in the numbers, and you can find that in the same frequency range, you probably expect order of 100 black holes in the Milky Way, black hole binaries, and several tens of thousands neutron star binaries in the Milky Way. Probably you also expect some neutron star black hole binary, but we haven't seen any of those up to date, so it's very hard to assume a number for their merger rate. Okay. Right. So these are the numbers that we're dealing with. So 100 millions white dwarf binaries in the Milky Way, hundreds, maybe perhaps black hole binaries, and several tens of thousands neutron star binaries. So those are going to be in the LISA band. I'm not claiming anything about their detectability or not. They're just going to be in band. Okay. So this is an example of how a signal would look like. This is a fairly old plot. You see from the very fancy style of the labels by one of the early papers by Heisen-Ellemans. And so this is essentially is the superposition of several million such sources. And you see these spikes here are each spike is an individual source. So you have this forest essentially of signals. And at some point they become so dense that you cannot resolve, you cannot separate the signals among themselves, and you're just left with an unresolved background. Okay. So one of the challenges of LISA, of course, is well, maybe one of the easier maybe is to actually separate as many as possible of these sources and measure their parameters. And so we think, so this is an example of once you took this signal here, you actually start to subtract sources. And of course, the signal builds up as the mission goes on, right? So as the mission goes on, you build up SNR, so you can subtract more and more sources. And what this plot shows is actually what is the residual confusion noise that is left from the sources that you cannot resolve as a function of time, right? So at the beginning, you can resolve, this is just after, let's say, half year, you cannot resolve that many sources, and you're left with this level of the background noise. But as the time goes on, you see you can resolve more and more sources, and this unresolved background goes down to this level here, okay? So the idea is that as you build up SNR from the individual sources, you can resolve more and more of them. Now, of course, one thing that you want to do is to measure the parameters of the system. And okay, I put here like the more general case. So in how do you extract the parameters from the detection? So the actual amplitude of the source in the detector, right, is a combination of the polarization amplitude plus and cross of the signal with the antenna beam pattern of response function of the detector, right? And so you know that for LIGO, essentially these are just fixed function depending on when the source arrives, because the signal is usually much shorter than the typical time over which the detector moves, right? Because, for example, even the longest signal that we've seen with LIGO was a minute in band, right? And so in a minute, the Earth doesn't rotate that much that you don't have a time-dependent beam pattern function. But things are extremely different for LISA, because, for example, white dwarf binaries, they live in band for all the mission lifetime, and if the mission lives, the mission lifetime is 4 years, okay, you have 4 years of data, and the antenna beam pattern changes because the detector is going around the sun, trailing the Earth, and rotating on itself, right? So you have a complicated pattern function here. So you know that you're probably familiar with the polarization amplitude of the wave, and you know that they depend on the masses and the frequency. They depend on the distance and the inclination angle. So, and you know that there is some, degeneracy between distance and inclination angle, right? So it's that makes it hard to measure the distance if you cannot separate the two polarization. The antenna beam pattern essentially encodes all the information about where the source is relative to the to the detector, so essentially the sky localization of the source and all other stuff. And the phase evolution of the source encodes all information about the intrinsic parameter of the system, the individual masses, which are they don't enter as individual masses in the formula. They enter as a chirp mass and symmetric mass ratio, but that that doesn't matter. You can extract the individual masses, you can extract the spins, you can extract the eccentricity, and so on. So for the more complex binary that you can think of, let's say driven by GR only, you end up with 17 parameters. Okay, so the idea is that you can actually measure a signal good enough that you can dig out all these parameters and measure the parameters of the system. Now, for white dwarf binaries, actually, most of this stuff is essentially irrelevant because you measure maybe the frequency and the first derivative or the second derivative of the frequency, so you end up with much less parameter than this. Nonetheless, these are some very old numbers for again for these galactic binaries. We think that these are actually a little bit pessimistic, but we can probably resolve order of 20,000 such individual binaries. And for these 20,000 binaries, we can measure for several thousand of them. We can measure the sky location within a square degree. Okay, which is important because we can look for counterparts. Those are white dwarf binaries in our Milky Way, right? So if we know the location, we can actually look for counterparts of these objects. We can measure the f dot and the f double dot for some of them. So we can measure the f dot for several thousands. This is also important because we know what the f dot should be because of gravitational wave emission, right? But many of these systems are going to be, mass transferring systems. So for example, they can have an inverse chirp because they are transferring mass from one object to another. So instead of having the frequency going up with time, you have a frequency going down with time. So, and that of course is going to give us a lot of information about the way this mass transfer process works. Okay. Oh no, in this case, yeah, I mean, 17 parameters are if you have a point masses GR only systems, yeah. But in this case, these are relatively low SNR system. The evolution in frequency is not that big, so you can't really measure much of those parameters, right? You probably measure the frequency and the derivative of the frequency, and that's it for most of them. Right. So another interesting type of sources, which are, it's the same class of sources, but another type, in fact, are sources that will actually enter, okay, let's start again. So those binaries I was talking about are only detectable in the Milky Way, right? We cannot see white dwarf binaries or probably not even neutron star binaries in other galaxies, right? However, we can see black hole binaries much farther, and that's simply because they are more massive, so their signal is, they have higher SNR. And in fact, the first detection by advanced LIGO brought to attention the fact that these objects are probably fairly, some of them can be fairly massive. Like the first detection were two black holes of more than 30 solar masses, right? And you can see these systems in LISA up to several hundred megaparsecs. So you can actually see them in many galaxies outside the Milky Way. Another very interesting thing is that, well, being very massive, the first detection of advanced LIGO in Virgo, the frequency drift, you remember this formula here, is also quite big, right? So this means that, right, if you can project actually back in frequency the evolution of GW15 or 914, and you can see where it was as a function of time. And what it turns out is that the chirp mass is so big that 5 years before coalescence, it was Mach-on in the LISA band, right? Which opens a very, it was a bit of excitement about that, and because it opened the possibility of actually seeing the same system in LISA and in LIGO, with some week of difference. Because if you look at this system here, for example, you see it starts in the LISA band like a few years before merger, and then, well, it's actually, it's been there forever, but suppose you turn on the LISA detector, you see it in band for a few years, Then it gets out of band, let's say maybe a month before final coalescence, and then after a month it appears in the LIGO band and it merges. Okay. So this is a very, so these are the sources you were referring to. I should point out that there is a whole population of these black hole binaries, and actually the ones that sweep from the LISA band to the LIGO band and are detected in both are actually only a small fraction of them. Okay, the vast majority are just sources that, they're just slowly spiraling at lower frequency. Okay. Anyway, so this is actually what I was just saying. So this is a nice plot from Kyotoko and Seto 2016 that show the frequency distribution essentially of this system in the LISA band. So let's take the red curve here, which is probably the most relevant for the current design of LISA. So what you see is that you can roughly draw a line here, which is between 10 to the minus 2 and 2 10 to the minus 2 hertz. And that's the line that defines the separatrix between whether your source is going to sweep in band and merge in the LIGO band, or your source is going to stay in the LISA band for all the detection time. Okay, because we know again that this formula here. So if you are at low frequency, you just stay there. If you are above this frequency, which is it depends on mass, etc. But just the order of magnitude. Just to have an idea what the separation is. So you see that you have, like what I was saying before, you have a fair amount of sources, maybe up to 100 to several, that are at frequency above this cut, so they're going to merge in the LIGO band. But then you have the vast majority of them pile up between a few millihertz and 10 millihertz maybe, and they can be as many as several hundreds or maybe thousands. Okay. So we expect the vast majority of these sources to be actually, slowly spiraling, and a subpopulation of them to actually go into the LIGO band. But that's just simply a continuity equation, right? You're seeing them in band, and they are evolving in frequency, and every now and then you have one that goes into the LIGO band and merges. So we can, so how many we expect in the LISA band? These are some calculations that I did a couple of years ago. So the most relevant points are the one here for current detector design, assuming 4 or 10 years of mission operation, and this is for 2 different population models. So you see, you might expect several hundred to maybe 1,000 of these sources with SNR higher than 8, and maybe a few tens to up to 100 maybe if your LISA detector runs for 10 years. Of systems that actually will cross into the LIGO band and merge in LIGO. Well, I'm saying LIGO. We are in France. I should say LIGO Virgo. LIGO Virgo Cagra Indigo. Right. So you already seen this formula because Neil showed it before, talking about supermassive black hole binary. As Neil pointed out, also for the sources, it's all the same, right? Black holes are, you just vary the scale, but the type of signal is the same. So if you accumulate many of these stellar mass black hole, at some point you cannot resolve them anymore, and you end up with a, unresolved background. And this unresolved background has this form here that was already shown by Neil, having like a, in the limit of a circular gravitational wave driven binary test an f to the minus 2/3 power law. And it turns out that this might also be detectable by LISA. And actually with an SNR of order of several tens or maybe up to 100. Okay, so you can also detect the overall signal from the sources that you cannot resolve. Now, can detect is a big statement. I mean, it's going to be above the noise level of your detector, right? If you integrate the signal for long enough time, whether you are able to separate that from other backgrounds and other confusion signals, that I don't know exactly. So, yes?
So here you're only talking of confusion noise for stellar black holes.
Yeah. Right, so why they're interesting? Well, they're interesting because you can do a lot of stuff from them, with them. So, for example, you can do detector cross-calibration. If you're particularly lucky, this might be possible to, you can use these sources in the LISA band to calibrate, I mean, the source is going from the LISA to the LIGO band to calibrate ground-based detectors if the SNR in the LISA band is high enough, right? So the problem with the LISA band is that, so these are, I mean, you see them only at low, you know, if they are close by, and the typical, they're just above SNR threshold. So it's very rare that you have a system with, you know, SNR of 100 or so, right? But if you have one, so if you have a signal that you can, so for which you can determine the, you know, the amplitude of the signal with percent precision or better in the LISA band, and then you see it in the LIGO band, right? You know exactly what the amplitude of that signal should be, and you know what is the current calibration precision of ground-based detectors? 10%, right? 5-10%. So you might do, you know, probably this is going to improve in later years, in the next years, but you know, you can have a very nice cross calibration check with these sources. But it's probably unlikely that you have such an ISNR system. So that's an interesting thing that goes under the name of, you know, multi-band astronomy, because you can use these sources as cross calibration. Of course, another thing that you can do is you can use LISA. You know, actually, I changed the thing in the slides. You have LVK is LIGO Virgo Kagra, so everybody's happy. I didn't put Indigo because it's another LIGO, right? It's LIGO India. Anyway, so you can, for example, if you have a particularly interesting system, like a particularly massive binary that is, you know, is going to merge at some point, you might not want to miss them, right, in your ground-based detector. So you can alert with, you know, a few weeks in advance saying, you know, okay, there's going to be like probably 150 solar mass, 100 solar mass binary merging at that time. Please make sure that your detectors are on, right? So of course you can inform with the parameters, and I will show what are some of the parameters of the source, and you can also tell. So you can actually prepare ground-based detectors for the detection of these systems. On the other hand, of course, the ground-based detectors are actually much more sensitive to these kind of sources than LISA is. So if you look back at this plot here, where is it? Right, so the dark blue are sources that have SNR higher than 8 in LISA. The pale blue, they have SNR between 8 and 5. So let's say technically, those wouldn't be bona fide detection in LISA, right? You might have something that is above the noise, but you know, you're not quite sure that this is the source. But then you see it merging in LIGO a few weeks later. Okay, so you can go back and dig in your LISA to essentially, you know, confirm sub-threshold systems. And you can probably do it for many of them. So which, you know, might be interesting to, you know, subtract some of the source and see what is below them. So I don't know exactly what you can do with them, but you know, you can certainly do this job. I'll get that in a second. So just, yeah, next slide. So as I said before, you know, you can actually get the property of the wave. You can get the property of the source from the waveform. This is a nice GIF from Walter del Pozzo, which shows how the waveform changes by changing the total mass of a system, right? So if you just can measure the waveform well good enough, or you know, phase up the waveform good enough, you can actually measure the property of the system. And one interesting prospect for this detection of these multi-band sources is that actually you can measure some of the parameters in LISA with stunning precision. So in particular, the time to coalescence is going to be of the order of few seconds. And that's, if you think about it, that's obvious because you are essentially phasing up. So the typical frequency in the LISA band is 10 to the minus 2 hertz. You see for several years, so you have like 10 to the 6 cycles, right? So you determine the phase to that accuracy a few weeks before merger. So essentially, what you get in the precision of merger time is of the order of few seconds. You can do the math, is exactly the number that comes out of it, which is good, right? You can say, okay, merger of whatever, or another thing, you can measure the chirp mass, well, redshifted chirp mass, but the redshift is very small, so that's good, to like a millionth of a precision, right? Relative precision. So you know exactly the masses, and you know also the symmetric mass ratio. So you know you can separate the individual masses to like 1% or better. And also the sky localization is going to be, in general, quite a bit better of what you can achieve with even with the network of ground-based detector. Okay, with the network of ground-based detector, you can get like, few square degrees for the best sources maybe. But here you can get, some of the peak of them is like to zero point 0.1 square degree. So that's particularly nice, I think, because you can actually tell your ground-based friends saying, okay, a week from now, 2 p.m. plus minus 10 seconds, exactly there's going to be a 50 solar mass black hole binary emerging, right? And then what's the difference between, this is not, many people can think, okay, this is not as we already detected gravitational wave counterpart from a neutron star merger, right? So who cares, right? So first of all, these are black hole binaries. So maybe, depending on if you are a fundamental physicist or an astrophysicist, you can say they are more or less interesting. So if you are an astrophysicist, you say, well, they're less interesting because you don't really expect the counterpart. If you are a fundamental physicist, you say, well, if you find a counterpart, a burst of some radiation that comes from a merger of black hole binary, that might be a big deal, right? Because I don't think really you expect that from any standard theory of gravity. So the thing that is different here is that if you can alert things like Athena, if it's up there, LSST, whatever, JWST, whatever you have, right, with weeks in advance, telling with some precision where they have to point at the exact time, right? It's much easier to schedule things than, okay, we are seeing the thing like 20 minutes in band with the 3G detectors, and we can say we can see where they are, but you just have 10 minutes to point your stuff, right, to see something at merger. So here you can actually get prepared and go as deep as you can with all the probes of all the wavelengths that you can, because you have all the time to prepare. So I think this is the nicest thing about this multi-messenger stuff. You had a question, or? Oh yeah, no. Is a mock population of detections. So so the thing is that the precision of certain parameter, okay, it scales with SNR, but the uh, the normalization, it's really different for many parameters, right? For example, even if you have an SNR of 10, right? If to detect that system with an SNR of 10, you have to phase up 1,000,000 cycles, right? You need that, it means that by detecting it, you had phased up successfully 1,000,000 cycles. So it means that you are measuring f dot, etc. very precisely, the phasing very precisely, so you are getting the mass to 1,000,000 precision. That's the reason why we'll see in a second, every detection of an emery, extreme mass radiation spiral, is a detection of a good emery. Because to dig them out of this, from the noise, you need to phase up several tens of thousands of cycles. So you automatically measure parameters like masses of the sources with astonishing precision. Yep. Yeah, yeah, that's also what I say, but when I say that, ground-based people, they always pick on me. Yeah. Well, maybe hundreds, so, right? Because it's now, I mean, GW15 and 14 was what, 20 something SNR, and it has an SNR of 6 or 7 in LISA. So if you take the O1 sensitivity and you, I don't know, multiply by a factor of 5 maybe to go to A plus, because it's, yeah. So, you can have, a couple of hundreds maybe. So, yeah. Um, okay, so what time is it? What, 5 to 12? Any other question? We're doing well? Okay. Right, so let me just skim through some other stuff that you can do. For example, an interesting thing that you might have noticed since we detected something, there were like thousands of theoretical paper claiming, of course, we can form this system through this channel, through that channel, through that channel. We can tweak our parameters and just reproduce the observation. So, which is a nice and interesting exercise to do, and so people are actually starting to put together astrophysical scenarios to explain these sources, right? One interesting thing that you can do with LISA is you can get some extra bit of information about the properties of the system that you hardly get from ground-based detectors. So you might know that there are two leading scenarios to form this system. One is the field scenario, where you actually start off with the binary in the field. You go through all the evolution, common envelope, etc. Neil showed one of these plots yesterday, and then you just form a compact remnant and binary, or a compact binary of remnants, and they eventually merge. Or you can form them in a star cluster, whereby you just form binaries by direct capture, and then this binary might have the properties that are led them to coalesce within an Hubble time. So an interesting difference between these two scenarios is that they predict different eccentricity distributions for this system. And you can think about that as follows, right? So you have a binary that evolves undisturbed in the field. There's going to be tidal interaction between the two objects, so the orbit is going to be fairly circular. Then, of course, you can get some supernova kick when you have like a collapse into a black hole that might get some eccentricity to the orbit. But in general, you expect this system to have a small eccentricity. Whereas if you are capturing objects dynamically in a cluster, you expect eccentricities to be in general larger. Okay. However, we know that gravitational wave emission circularizes binaries, right? And by the time you get to the 10 Hertz, where you start to see them with ground-based detectors, there's going to be essentially circular. And this is what is shown here. So these are distribution of eccentricity at 10 Hertz for different models. And you see that most of the models predict eccentricities that are between, this is like 10 to the minus 7, okay? Only with this scenario where you have like Kozai resonances and stuff, you get a tail of eccentricity that is above 0.1, which is roughly what you can measure with ground-based detectors. But this information you're not going to get, at least not for many sources in ground-based detectors. However, and these I'm here and cut out, but if you project this eccentricity distribution back in frequency, and you see what the eccentricity was in the LISA band, you see that essentially a large part of the sources have eccentricity which is higher than, let's say, a part in 1,000. Okay, and that's an important number because a part, this is something that we measured with a paper with Nishizawa and Berti and others, is that a part in 1,000 is essentially the level of eccentricity that you can measure with LISA. Okay, if you have anything that is more eccentric of 0.001, you're going to measure that eccentricity with LISA. Okay, so that's particularly interesting because then you can measure the eccentricity of this population, and it can become a very powerful discriminant between different formation channels. Okay, that you can add to other information that you get, for example, from spin configuration and other things that you measure instead in ground-based detectors. Okay, so also here there is an important synergy between ground and space-based detector. Another thing that I wanted to point out that is true for these black hole binaries, but it's also true for all the other sources, and this is actually more a spot for LISA, is that LISA is an instrument that is maybe not the best instrument for cosmology or for cosmography, if you wish, but it is a unique instrument for cosmography because you can use different sources at different redshift to do cosmology at all redshift in the universe, from the local universe up to redshift 5 or 10, which is it's something that is pretty spectacular. Maybe the precision is not going to be as good as W first when you get like 10,000, 100,000 supernova, etc. But well, if you understand the systematics there. But you can actually you have sources at all redshifts, okay? And in some, so you probably know. I don't know. Did you have some lectures about standard sirens stuff like that? So essentially, the idea is, for those of you that haven't heard about this, the idea is that gravitational waves are very powerful. Gravitational wave sources are particularly powerful because from the gravitational wave, you can measure directly the distance to the source, okay? Which is something that usually you don't measure electromagnetically, okay? The disadvantage of gravitational waves is that you don't measure the redshift, okay? However, the main idea is that what was realized for the first time um, with the GW17 or A17 is that, okay, you get the measurement of the distance from the gravitational wave. If you get a counterpart, you can use emission lines, absorption line, identification of galaxies, whatever, to measure the redshift, right? And now you can populate your redshift luminosity distance diagram, right? And you can fit a cosmology to that. And this is what you do essentially with standard candles, where essentially you use the ansatz that these explosions are all the same in luminosity, right? And you apply correction, etc., to actually use the luminosity to measure the distance, and then you measure the redshift from the lines, and you do the same plot with supernovae, for example, right? But with gravitational waves, you have, I would say, you have a much more trustworthy measurement of the distance because, you know, it comes from GR that is pretty damn good. So it's not like you don't have to apply some model where you rescale your light curve from some supernova model, etc., right? Now, the problem, though, is having counterparts. And this might be crucial for some of these sources. For example, the supermassive black hole binaries, you can see them at high redshift. We will talk about them tomorrow. And you can hope that they are in a dense galaxy post-merger galaxy nucleus, right? So you can hope that there is a lot of gas around, and there is going to be some signature of the merger, so you might detect a counterpart. If you detect a counterpart with a massive black hole binaries, then that's pretty awesome, because you have systems at redshift higher than 1 from which you get, you know, a measurement of the redshift and the direct measurement of the distance with LISA, and typically the measurement of the distance with LISA is so good that you are limited really by weak lensing, right? So you get sources with a distance measured within like few percent, because that's the error in weak lensing, and you have of course an exact measurement for any purpose of the redshift from identification of the counterpart. So with the extreme mass relation spirals and these LIGO-like black holes, you can actually see them at lower redshift. MRIS may be up to redshift 1. We'll see that in the last 20 minutes of the lecture. And this stellar mass black hole may be to redshift 0.1, 0.2. The problem there is that you cannot rely on the fact that you're going to see a counterpart, right? Because you have two black holes merging in relatively vacuum space. You don't get anything. You get the extreme mass relation spiral is different from a massive black hole binary merger, because you have a massive black hole and you have a compact object that is whirling around, right? And that compact object has not been brought in by a merger of a galaxy. So there's no reason really to think that there's going to be a particularly, gaseous rich environment. Plus, the signature of a tensor mass black hole at cosmological distance accreting gas is going to be, nothing really interesting, right? So you cannot rely on the fact that there's going to be a counterpart for these sources. So what you can use is, you can apply a statistical method. So since I showed you before that the sky localization for these sources is pretty dang good, right? If they are a low enough redshift, you might have only a handful of galaxies in the error box of your detector. And then you can apply a statistical method. Of course, there are assumptions here. You assume that your source is in one of these galaxies, which is a fairly good assumption, I would say, fairly motivated assumption. And then you just essentially stack, the probability distribution of the redshift distribution of your post-plausible hosts. And of course, this redshift distribution changes for the assumed cosmology. And when you get the right cosmology, let's say they line up together. Okay, so if you can think of it as, if you have like a single source in your error box, it's very easy, right? So you have a single source in your error box, then this is the probability of redshift for your error box. So this is redshift here, right? This is probability. And so you just have a delta function, right? And if you have the wrong cosmology, you add up these two probability distribution. Okay, you get 0 everywhere, because the delta function in one is just null by the 0 in the other. Only if you get the right cosmology, these line up at the same, at the same redshift, right? And then essentially you get your right cosmological parameter from there. Of course, you just don't have you don't have like delta functions because you have error measurements, so everything is broadened and you have multiple galaxies, etc. But this is the basic idea. Okay, so you can use statistical methods, and we demonstrated this for this stellar mass black hole binary, of course, on mock catalogs with Walter and the Potts and other collaborators, and you can maybe measure H naught to 5%, few percent, only with these stellar mass black hole sources. What we are doing now, we are trying to add up essentially all the sources from black hole binaries, extreme mass radiation spiral, and supermassive black hole to see how well you can do cosmology with those sources. Yes, yeah. Right. Yeah. Right. Yeah, so the answer is okay. The answer to this to the first question is yes, right? So you expect. I mean, the answer to both questions is yes, in the sense that you expect them to be in gas-rich environments, and you expect the binary to prompt some electromagnetic signature that is distinctive with respect to a single black hole. The point is, what that distinctive signature is, nobody really knows. I mean, you can dig in the literature, you can find like 100 papers talking about counterparts of black hole binaries, and some of them are orthogonal. So we really hope that we identify something in the end that can signal the presence of this system. So it's really we can talk about that maybe later in the afternoon. I want to finish the lecture now, but there can be like a couple of lectures just dedicated to what are the possibilities in this thing, but we really don't know much. Neil, do you have a comment? Right. Oh yeah, yeah. Oh yeah, yeah. Yeah. I mean, I wasn't claiming that we invented this. I mean, the first idea of detecting these sources by burning in '86, right? Actually came up with the idea that you can use this statistical method if you don't have a counterpart. Yeah, yeah. No, I wasn't saying that we invented it. I mean, it's like a 30-year-old idea. Um, yeah, yeah. Sorry. And actually, I think there was a paper like a few days ago, right, or like a couple of weeks ago, where I don't know if was it the LVC or a subset of the LVC where actually they did the it was on the archive. I mean, I saw it on the archive. I'm not in the collaboration. It's a subset where they did this exercise, right? Of course, you have a counterpart, so you can do it better with a counterpart. But okay, let's do the exercise like Bernie style. Suppose that we don't have a counterpart. We know what is the sky location. We have the distribution of galaxies, and still you get, well, the measurement is pretty poor because it's only one source. But you can do the exercise. Oh yeah, yeah. I mean, this exercise, for example, the one that we did here, we consider the fact that the distance measurement is actually pretty poor. So you don't, you have to consider a big volume, so you have a lot of galaxies in your error box. Um, I guess so, because of course, if in the end, the statistical method is limited by the fact that if you have too many counterparts, uh, galaxy counterparts, that the statistical information that you have, it's very poor, right? So, if your delta L over L is 50%, then you essentially have like all the galaxies from 100 megaparsec to 200 megaparsec says, right? If you can shrink that by a factor of 10, you might end up on. I mean, it's also a very a statistical method, right? So if your error is small enough, you might end up with one galaxy in your error box. And actually, we find that for extreme acceleration spirals, this is the case sometimes. So sometimes, since the sky localization is measured at a comparable level with respect to those, but because they are usually higher SNR if you dig them out of the data, the distance that you can measure them is like sometimes is a few percent, sometimes is even 1%. And at that point, you have 1% error in the distance, you have like, you know, 0.1 square degree in the sky, you know, there is a chance that you have only one galaxy in there. And, you know, at that point, it's like you have a counterpart, you know, the redshift, so which is, you know, pretty cool. Okay, so, well, all right, let me move on to the last topic that I wanted to cover in this lecture, which are extreme acceleration spirals. Okay, so this is just, you know, why it's interesting. Okay, there are a few things why these are interesting. First of all, LISA is sensitive to mergers, let's say in spiral, of stellar mass black holes into black hole binaries of masses of 10 to the 4 to 10 to the 6 solar masses. And this is exactly the regime in masses where we don't know much about the population of these massive black holes. We don't know much about, you know, if they inhabit galaxies, the center of dwarf galaxies or not. So this is also important because, okay, we might get more statistics about these objects with electromagnetic observations in the future. However, those rely mostly on detecting the accretion, okay? So you're gonna get the properties of a sample, of a bias sample, which are the black holes that are accreting. Whereas, of course, there is no reason, well, there are models where, you know, you connect extreme acceleration spiral to galaxy disks, but I don't want to talk into that. But in general, for any galaxy, in the center you have a cluster of stars, you have a cluster of compact objects, and you have a massive black hole, and every now and then you form an extreme acceleration spiral. So there's no connection between a specific time in life of the galaxy and the occurrence of this extreme acceleration spiral. So they're going to provide you with an unbiased sample of the population of these stellar mass black holes. So this is why it's very interesting from astrophysical side. From the fundamental physics side, I mean, these are probably the most, for many reasons, the most exciting objects because you have essentially a test particle that is whirling around space-time for tens of thousands of cycles. So that's is essentially a test particle free falling in Kerr, right? If these black holes are Kerr. So you can measure things like Noether theorem, the metric and stuff like that to a ridiculous precision. And you know, there's no other object for which you can do this exercise at this level. So this is why they are also super interesting for fundamental physics point of view. Okay, let me give you some context. Okay, so essentially we are talking about the galaxy, let's say something like the Milky Way, maybe slightly smaller. So those are the typical properties of this system, right? So we have like a typical density is 1 star per 100 parsec cube. Velocity dispersion of, you know, 100 kilometer per second, and the relaxation time is something that I introduce in a second of the order much larger than the Hubble time. Okay, so that's a typical galaxy. So if you zoom into the center, so this is actually zooming in the center of the Milky Way, you find yourself in the central star cluster of the galaxy, and there the density is much larger. So you have like million stars packed in a parsec cube. Okay, so you know that the closest star to the sun is Proxima Centauri, which is like a parsec away. Okay, so instead of having the sun and Proxima Centauri in that volume, you have a million stars. Okay, so that's the type of densities we're talking about. Velocity dispersion increases because your potential start to be dominated by the central massive black hole, and the relaxation times are shorter than the Hubble time. And so what happens if you just zoom in another 7 order of magnitude, this is the horizon of the black hole, at some point you might capture an object in a very eccentric orbit around this system, okay? And this is what gives rise to a typical extreme acceleration spiral, okay? So let's put in some number. So the typical influence radius of a black hole, so the influence radius is essentially a radius where your star starts to feel the pull of the black hole, okay? So because the stars is moving in a sea of stars, and and it has a velocity dispersion, so it has like an energy which is of the order of 1/2 sigma square, right? So that's the typical energy per unit mass of the star, right? If you get close to the black hole, the potential energy it feels per unit mass due to the presence of the black hole becomes larger than this. So if you equate the two, you get the influence radius, which is gm divided by sigma square, okay? And is of the order of a parsec, roughly. So the central parsec of the Milky Way is dominated by the potential of the supermassive black hole, okay? Now, so let me draw a nice cartoon that I don't have here. Well, I probably have it later. I should actually pull it up. It's this one here, right? Okay. So you have, let's say, a central object here, and you have all this bunch of stars, okay, around. So this is a very dense environment, so stars encounter each other, right? So the trajectory of a star is not going to be an ellipse or an ellipse with precession because you don't have a point like potential, but the trajectory of a star is going to be deflected by the fact that you have encounters with other objects, right? So what these encounters do is to change the property of the orbit and diffuse the orbit in energy and angular momentum. And in particular, it turns out that it's much easier to diffuse orbits in angular momentum than in energy, right? So what happens in the long term is that you can get an orbit like this, and you can just move it on a much more eccentric orbit, right? Or on a much more circular one, okay? So this relaxation, so the relaxation timescale is essentially defined more or less. So suppose you have a star that has a velocity vector like this, okay, is defined by the time that it takes to get to this velocity vector, essentially change it by 90 degrees, essentially, okay? So when the collective action of your encounter significantly changes your orbit. So this, you can actually work out from two-body scattering theory what this is. You can go to, take B-net remaining relaxation time. There is all nice derivation. And this is more or less what you get. And it's interesting to see the dependencies here. So it depends, so it's order of, the order are hundreds of millions of years in these units. You see that it goes with the velocity dispersion to the third power. And this is kind of intuitive, right? Because if the velocity dispersion is much larger, right, so your two stars are typically moving one with respect to each other at much faster velocity, so the scattering cross-section becomes smaller, so the collective effect, the collective deflection that you have because of this encounter is smaller. And it turns out that this dependence goes with the velocity to the third power, right? And of course, well, it depends on the mass of the objects, because more massive object deflects more, of course. And it depends on the density, again, because if you have a density, if you have a more dense environment, you experience more encounters, okay? So now, another interesting thing in galactic nuclei is that because of this relaxation, in fact, you have the process of mass segregation, and this is what this cartoon here was. This is a snapshot of a simulation was supposed to be. So so these are stars, are not black holes, but the dots are proportional to the mass of the stars. And these are snapshots of a simulation at the beginning and then after some relaxation timescale. And you see that the massive objects have clustered in the center, right? So the point is that, in general, massive objects cluster around the black hole with a distribution of density that goes with R to the -2, okay? It's more or less like an isothermal sphere, okay? So they are severely clustered toward the center, okay? So this is the density, right? Goes with R to the -2. What is the velocity dispersion? Well, you are well within the influence radius of the black hole. So the velocity dispersion is not a constant, but it increases as you go closer to the black hole, because it's like, it's dominated by the Keplerian potential of the black hole, right? So the velocity dispersion goes inside the influence radius, goes with R to the -1/2. So you can put these scalings here, and you see that the relaxation times goes with R to the 1/2, okay? So it's longer, it's slightly longer as you move farther from the black hole. But what is important here is that, it's not really a big it doesn't have a huge dependence on the radius. Okay, it's pretty much constant with it. And the typical order of magnitude you will see is of the order of several gigayears. And actually, depending on the property of the cluster, your relaxation time can be shorter or longer than the Hubble time. Now, why I'm telling you all of this crap about the relaxation time? And it's because, of course, what's happening? Okay, you are deflecting the orbit of the black hole, but remember there is a massive black hole at the center, right? So what you're interested in forming an emery is the following. Okay, I have some black hole that is on some trajectory, right? And then it gets deflected by an encounter onto an orbit that passes very close to the central massive black hole, so close that it emits a burst of gravitational radiation, and this orbit gets captured and shrinks significantly its eccentricity, right, being bound to the black hole. Now, what is the trick that you have to do to form an emery is the following. Well, you are just deflecting this object into the, let's say, strong influence region of the black hole. Now, you emit a burst of gravitational waves, and then you fly out again. If you get deflected by another close encounter, you can be kicked out of this orbit, and your emery is lost, right? So it's fine-tuning between the time it takes to this object to circularize because of gravitational wave emission thus being captured, and the timescale, typical timescale at which this object is scattered within, in and out of this lost cone is called region, right? Now, what are those timescales? Well, you can write the circularization timescale as E, which is the eccentricity of your capture orbit over d dt, which has this expression here, and it has these dependencies on the masses, on the separation of on the semi-major axis of the orbit, and on the eccentricity. And you have actually, in the condition to form an emery is that this circularization time is smaller than, well, this is a constant of the order 1 minus c, the relaxation time. So why 1 minus c? 1 minus c because the relaxation time scale is the time scale to, flip this vector, right? But to get in and out of the lost cone, you don't need to just flip this vector, right? You just need to change it by an amount which is of the order of the sides of your lost cone as you see it from distance r. But this size decreases with 1 minus c, okay? So you have to balance these two timescales, and this is what defines the condition for forming these extreme acceleration spirals. Now, if you do the math for a typical stellar distribution, this is what you get. So this is 1 minus c. This is separation. This is semi-major axis, sorry. This defines an orbit that plunges. So this defines an orbit that goes radially into the black hole, okay? And the red line actually defines the separatrix where your scattering timescale is longer than the actual circularization timescale. So what's happening is that your binary is being scattered in energy and angular momentum, but mostly in angular momentum, sorry, your black hole. At some point, if you hit this red curve here, you get captured and you circularize quickly enough that you're not kicked out anymore by this region, and you form an extreme acceleration spiral, okay? And the bottom line that I wanted to point out, I'm just, skim through this because I'm running out of time, is that, well, for a typical rho to the r to the minus 2 distribution in density, so the number of objects per unit radius is constant, right? Because, integrate over a sphere, because the r square cancels. But this means since we like logarithmic distributions, so we like to see if our things come from, 1 AU, 10 AU, 100 AU, right? So this means that the typical emery comes from this critical separation accrete here, because this order of magnitude in separation is where you get 90% of your sources, right? And I forgot to mention, you see that this is of the order of few, hundred of a parsec, few hundred of a parsec. And also, it's easier to be scattered in and out at that separation because of the relaxation timescale scaling that we saw before, together with the fact that you have to dump it by 1 minus c. So the bottom line is that most of your memories are formed at this intersection between when, at 0.01 parsecs, okay? And then, what is the rate at which you form it? Well, you can approximate it as the number of compact objects within that radius divided by the relaxation time within the radius, because the relaxation time is going to tell you what is the time scale at which you actually get all the objects within your, lost cone. Now, for a typical Milky Way cusp, you have like 10,000 star. We expect to be 10,000 stellar mass black hole within the Milky Way. The typical relaxation time for those subpopulation is of the order of 10 to the 10, 10 to the 11 years. So if you put together the numbers, and you can get that by the, if you just go back to the relaxation time here and you plug in numbers, then you expect a rate of 10 to the minus 7 per year, which is like 100 per giga year. If you do the calculation more carefully with some model, what you get is like, for a Milky Way type, a nucleus is like 300 per giga year. Okay, so this estimate is actually good enough. But this is so this was just to highlight what is the key physical process is just this balance between relaxation and circularization once you are on a capture on the orbit on a captured orbit. Okay, so this is what defines your memories. Now, 5 minutes. Okay, I can make it. I'm almost done. There are huge astrophysical uncertainties. First of all, when we try to estimate what is the memory rate for LISA, you have to take into account that LISA is going to see systems like in this mass range, 10 to the 6 to 10 to the 4 solar masses. The shaded area here are estimate of the black hole mass function. And you see that they stop roughly at 10 to the 6. And they start, most importantly, they start to diverge around 10 to the 6, right? So in the LISA range, there are essentially 2-3 orders of magnitude uncertainty in the black hole mass function only, right? So also, we don't know exactly what is the distribution of compact objects around these massive black holes. We don't know what is the fraction. So what I defined here is the condition for being captured. But a fair amount of these systems, instead of being capturing, are going to plunge directly into the black hole. And if you plunge directly into the black hole, of course, you have a burst of gravitational wave while plunging, but you don't build up SNR through thousands and thousands of cycles, so you're not going to see these systems very far away. So essentially, these events are going to be lost for LISA. Okay, so these are all uncertainties that we really don't know. And if you just try to, we just try to cook up some model where we factor in all of these, and we end up with memory rates that goes for, from several thousand, okay, the total rate, these are the detection, LISA detection, goes from maybe 10 per year to several tens of thousand, and the LISA detection goes, of course, we tweaked everything so that the lower limit was 1 per year, because otherwise it wouldn't look good, right? So you can probably, I'm pretty sure I can make up a model that has 0 events per year, but let's be optimistic. You go from 1 per year to several thousands, okay? But this is the range of uncertainty. We can have several thousand extreme acceleration spiral. We can have 1, okay? So, yeah, that's what we know. Right. I just want, well, this slide just show you, that the signal is very complicated, and this is how it look like in the power spectral density in the LISA mod data challenge. So you see here the galaxy, the white dwarf binaries. You see a supermassive black hole. This is an extreme acceleration spiral. So you see it's well below any other source and any other noise. So you really need to dig the signal out of the noise. So that's the and you're not going to have one of those. Maybe you're going to have thousands of those that overlap. And this is going to be a significant challenge, I think, for the data analysis people. Just wanted to finish up with a couple of interesting things that you do with those. So this plot here shows essentially the detection fraction of memories by LISA as a function of redshift. These are for different assumption of the waveform at the plunge, because let's forget about that. We can concentrate on this one. So you see, as I said before, you're probing essentially from Milky Way and few 10 to the 4 massive black holes, up to redshift, 2 or so. So that's significant. So a significant portion of the universe. And those are examples of the precision for which you can get some of the parameters of the system. So these 12 things here are just 12 different models. Never mind that. But what I show you here is that's the error to which you measure the spin of the central black hole, the supermassive black hole. So this number here is 10 to the minus 4. This number here is 10 to the minus 6. So you have, for any purpose, you have an exact measurement of the spin of the black hole, which is something that you cannot get by any other means. You cannot get it with supermassive black hole binary merger. You cannot get it from, X-ray fitting of your favorite spectral model to an accretion disk. So that's the only way you can get an essentially exact measurement of a black hole spin. And this Q here is the deviation of the quadrupole moment from Kerr, right? So you assume your black hole is not Kerr. What kind of deviation from Kerrness you can measure with this extreme acceleration spiral? And again, this number here is 10 to the minus 4. So you can measure tiny deviation from Kerrness of the space-time. So that's why, these systems are extremely interesting for astrophysicists and for fundamental physicists. Yes, these are the two different waveform models. Essentially, just to give a detail, is that the AKES, what we did is the is the typical standard analytic clutch. What we do, but these are we have spinning supermassive black holes. What we are doing in the AKS model, we are cutting the waveform anyway at the last stable orbit for a non-spinning black hole, so a 6M. Whereas the AKK, the waveform goes on up to the last stable orbit of a maximally spinning black hole, because most of them are maximally spinning. So you accumulate much more signal there, so you have much higher scenario. You can see more MRIs farther away. Yeah, yeah, yeah. Oh, yeah, yeah. I mean, no, it's not addressing that issue. But the kind of precision of measurement is going to be this type, right? If you get, if you have the waveform that is good enough. And the reality is probably it's probably in between these two. Right. So in summarizing, with the extreme acceleration spiral, you can expect, up to 1,000 detection. You can locate. Well, I didn't show all of this, but you can locate them in the sky fairly well. You can measure the distance, do cosmology, etc. You can measure the black hole spin to a ridiculous precision. You can measure both masses to a ridiculous precision. Eccentricity, deviation from Kerrness, so you can do astrophysics, cosmology, and fundamental physics. So these sources are going to be super nice for all these fields of physics, and also for dynamics of dense nuclei, because we don't know much about how this capture process work, and we're going to get a lot of insights about how these extreme dynamical processes work. And yeah, I think I'm done for today, right? In time, more or less. Right. Done. Thanks. I see the young students have questions. Yeah. Um, in order of seniority, go with.
So how bad will it be if you don't have good waveform models? So if it was self-force programming
Oh,
to actually connect all the tens of thousands of cycles.
I'm definitely not the right person to answer that question. Neil, maybe you know a bit more. I don't know. Uh, for some time.
But does it drop to zero, and just how bad does it get if you have one of those kludge models?
Something in between.
Of course, you never keep it to zero.
Hopefully not. Ah, that one, yeah. But that was from it was from the enchilada or something. I don't know. Yeah.
So it's not as frightening as it looks, right? Because, and it actually it's easy to understand. You showed how incredibly well the parameters of an emery is measured, right?
Right.
Which also makes them incredibly hard to detect because you have to dial
The exact
addresses
number.
and
Yeah.
spins to those values before you can actually get a match, right? But any two emeries, the overlap,
Yeah.
like they can get a product of
It's
anything
gonna
from
orthogonal. Yeah.
0,
Sure.
well, very close to 0.
Yeah.
So they don't, it's like the way signals are sent over telecommunication channels with encodings that make them essentially orthogonal. So you can multiplex millions of signals down a communication channel and still pull them out independently, right? Essentially, nature has done that for us with the emeries. They are essentially completely each one doesn't overlap at all with the others, basically. So the problem sounds bad when you show it.
Right. Right.
If you'd shown me 100
I,
emeries
I,
on there in all different, it would look like a horrible
yeah.
plot.
You. Yeah.
But actually,
Correct.
completely separate.
I guess probably the main problem is probably the waveform, right? To have a waveform that is good enough
Waveform.
to have a waveform that is good enough to dig
Right.
them out,
So,
right?
you know, for those of us that work on trying to pull out the signals, we show a plot like that to frighten people, but it's really not that bad. They think we're, doing magic wizardry to actually pull them out, but it's really not as hard a problem as it looks.
Cool. So any question for our students, from the real students?
So on the other hand, if you are so sensitive to so many parameters, in particular the sky localization and so on, and the signals are so long, how big must your template bank be?
Well, uh, what was the if you just do the naive calculation for Emrys, it's like 10 to the 40.
40, minus 10,
So it's not a manageable number, yeah.
that's why we don't use
But
templates.
you're not gonna use template banks for Emrys. You're gonna do other good stuff.
Unless,
Good stuff,
unless you had a quantum computer, there's no
right?
point. So we don't use those methods.
What do we use? Huh. What do you use in the?
Well, we use various variants of, we use stochastic samplers.
Right.
So there's papers by myself and Stas Babak and Jonathan Hare on this.
That address that problem, right? I mean, a grid search is not feasible for Emrys. Yeah. Good.
Okay.
Think go for lunch.